So in this video, we'll be talking about the t-test, which is kind of the basic starting inferential statistics test that many of us get introduced to. So there's a bunch of different types of t-tests. In fact, the very first one you might have heard of is a z-test, and though these are all different, and they are different, a z-test uses a z-distribution, a t-test uses a t-distribution, the basic idea of all of these is the same. So we're going to focus on the two sample t-test in this review. And again, if you're not familiar with these, I recommend you go back and check your notes from Basic Statistics 1 and Basic Statistics 2, Math 115 and 116 to check on these. And this is used with categorical independent variable, so your grouping variable. A common example might be something like, let's compare two different kinds of computers to see which one runs faster. So your categorical independent variable is going to be, are you having computer A or computer B? The dependent variable we assume is a continuous dependent variable, and so run faster, that would be in terms of time. Well, time, you can't run at a negative time, so time is actually going to be a ratio variable and certainly meets our definition of continuous. So an example, again, does hard drive A or B run faster? Now the thing with t-tests or z-tests is you need your categorical variable to have just two different groups, and we're going to talk about a different analysis later on that doesn't require this, but for t-tests we need two groups. Another thing we could do with t-test for the one sample t-test is we could just have a single group and compare that single group to a fixed number. So we could say, does hard drive A run faster than a certain amount of megabytes per second or something like that, in which we would only have a single sample and compare it to a fixed quantity. With a two sample t-test, we compare two groups to each other, and what we're actually comparing is the means of the two groups to each other. So writing our hypothesis is written as mean 1 is equal to mean 2. Note that these are using population parameters, not the sample statistics. So in my hypothesis steps, when I'm writing out the hypothesis, I'm writing mu, which is the population mean, and describing that. So my hypotheses are that the population mean from the first group, computer A, is the same as the population mean from the second group, and then my null, that's my null hypothesis, H sub 0, then my alternative hypothesis, H sub 1, sometimes this is listed as H sub A for alternative, but my alternative hypothesis is listed as the population means are not different. So I want you to, this thing about the population means, a lot of students take this as, oh, Dr. Florin's being super anal about notation. Yeah, but it's more than that. It's actually quite a bit more than that. What the interesting thing about the notation of the hypotheses indicates is something that many students, even after graduating, don't understand, and that is statistics tests population data. We only have sample data. The coolest part, the awesome part about statistics is we can take sample data and make conclusions about population relationships. I don't have to gather all data points in the whole population to check if the two means are equal. Now, if I had all the data points in the whole population, that's super easy. I calculate the mean of one, the mean of the other, and see if they're the same. Now, note this isn't close. This is, are they exactly mathematically equal? So if one is 3 and one is 3.00001, then we're going to reject H0 and accept H1, that they're not the same, because mathematically they're not the same. So that is important. We'll actually come back to that a little bit later. But again, a lot of students, they think, oh, this notation, this population notation, has something to do with, just being a jerk about notation, but it's far beyond that. It actually goes to the very heart and core of the point of statistical analysis, and the whole point of statistical analysis is to make population-based claims based on only sample data. That's why what we do is so cool and so valuable, that if there's 1 billion people in the population and I just sample 100, I can make claims about 1 billion people after only studying 100 using a few assumptions. Now, this particular set of hypotheses can be written in a second way. And the second way, just think about if you subtract Mewtwo from both sides. Mewtwo, I don't know if you're into Pokemon, but hey, Mewtwo. If you subtract Mewtwo from both sides, you get mu1 minus mu2 equals 0. So this is just like algebra 1 stuff, right? Not even, where you're just moving variables around. But this formulation is actually really, really handy because it helps give us a way in which we can say, I think this, that population 1 is bigger than population 2 by 5 or by 10 or something like that. So sometimes you'll see it written in this way and then equal to k. So we have the null is that this difference is equal to k. The alternative is that it's not equal to k. And that lets us test the difference between the two populations against a different value than 0. Now this is, believe it or not, is actually becoming best practice in statistics, where we don't want to compare to just the value of 0. We actually want to compare to the value that's the smallest value of interest. So what we want to say is, let's say I'm looking at a program that's, I don't know, trying to convince people to smoke cigarettes. And I don't want to run this program unless it convinces people to smoke at least 2 more cigarettes per day. Well, instead of doing a hypothesis test comparing against a value of 0, well, I don't care if it's different than 0. I don't care if the people who got my program smoke 1 cigarette more per day. I want to tell, is it different than 2? Is it bigger than 2? So I might actually make this comparison, and instead of comparing to 0, compare to 2. So that's something to consider here, is that this formulation really allows you to isolate the degree of difference that you want to compare, whereas this formulation, though it's a little more common and it kind of makes some intuitive sense, it only works if you're anticipating them to be exactly equal. Another piece of this is setting your significance level. Typically, we use the alpha at 0.05, and actually in real life, that's kind of all we ever do, 0.05. And you have to have a really, really good reason to not do that. I'll say in real life, again, as going along with this, we only want to compare to a value that's meaningful in real life, though in the textbook, we almost always make this comparison at 0. In real life, we tend to use a lot more confidence intervals than hypothesis tests. But we'll use 0.05, and actually, just to make sure you can, every once in a while, we'll give you a homework problem that asks you to compare at a different level than 0.05. All right, so the test statistic. So after you have your hypothesis, you have to calculate the test statistic. So what we do is we take the sample means for each and then subtract the hypothesized means. So remember that this is typically 0. This comes from the null hypothesis, and it's typically 0, but as we just talked about, sometimes you can set it to a different level. But by default, we use 0 there. And then you divide by the square root of s squared times 1 minus n1, or 1 divided by n1 minus 1 divided by n2. Note that s squared here is the pooled sample variance. What does that mean? That means if I took all of my data together, pooling it, so putting it all together, and then calculated the sample variance for it, that's my s squared. So what you're assuming is that each of the groups in here have a constant variance. You're also assuming the underlying distribution of the data is normal under some light assumptions. So this is distributed as a t-distribution with degrees of freedom of n1 plus n2 to minus 2. So another way of writing that is that the test statistic t is distributed as a t at the significance level 1 minus alpha over 2. So we're doing a two-tailed test here. Alpha divided by 2 implies a two-tailed test. This would be 1 minus alpha or just alpha if we were doing a one-tailed test. And then the comma, degrees of freedom in 1 and 2. So this is how we would find the critical value if we were doing a critical value. So the decision, well, if the test statistic is in the critical region as specified by the critical value, or if p is smaller than alpha, if you're doing the p-value approach, then you reject the null hypothesis. And if not, you fail to reject the null hypothesis. And that's pretty much it as far as it goes with making a decision about a t-test. So this has been a quick review on how do we conduct a t-test. In the next video, we'll talk about how do we do the chi-squared.